Hello everyone, welcome to ashatech.com, your engineering sciences channel. In this lecture, we are going to discuss bearings. A bearing is a machine element which supports another moving machine element known as a journal. So we have this bearing supporting another machine element, but this is basically what it means. It is put in such a way that it permits a relative motion between the contact surfaces of the members while carrying the load. So in most cases we introduce bearings where we have one member has to rotate relative to the other, but we also want to have it rotate while carrying the load at minimal forces of friction. Now we need to understand the terms that are applicable to bearing selection, because having understood what a bearing is, of course we may not explore all the kinds of bearings that we have on Earth in this particular video, but we are also going to look at these terms that are important to know while selecting the bearing. Because if you design your component or your machine element and the bearing is involved, you need to go ahead and select it. So from which designation are you going to choose your bearing? What specifications? What size are you going to choose? In other words, all these factors are at the back of your mind, but you also need to know the following terms. One is the static load capacity, and this is the amount of load a bearing will carry when at rest conditions. So we will see that it is going to be denoted by C naught, and this is basically that load that the bearing will feel or will support when it is not moving or when there is no rotation on those particular components that are utilizing the purpose of the bearing. Two, we need to also know what the static equivalent load means, and this is defined as the static radial load for the case of radial ball bearings or roller bearings, or the actual load in the case of thrust ball or roller bearings, which if applied would cause the same total permanent deformation at the most heavily stressed ball or roller and rest contact as that which occurs under the actual conditions. So if I'm to use maybe the static radial load in the case of radial bearing, I would say it is the static radial load which if applied would cause the same total permanent deformation at the most heavily stressed ball and rest contact as that which occurs under the actual conditions of loading. So we will also see how we utilize this in one of my videos, how you utilize this, how you can calculate it to go ahead and do the selection of the bearing. Now also the static equivalent radial load, for example, for radial or roller bearings under combined radial and axial or thrust loads is given by the greater magnitude of those obtained by the following two equations. One, we have an equation that looks at two combined effects of a radial and axial load. In other words, we use this formula for finding the static equivalent radial load or for finding the static equivalent load when you have radial bearings and you also have axial bearings. In other words, you have a bearing that supports radial loads, but you also have on the same particular system you have a bearing that supports axial or thrust loads. Then this second equation looks at a scenario when you have purely looked at the radial load, and it may give you this WR, especially when you don't have the actual loads, and therefore this X naught is equal to 1. The X naught and the Y naught are factors depending on if it is radial, then this X naught is the radial load factor, then Y naught is the actual load factor. Then we are saying WR is the radial load, WA is the actual load or thrust load, and the X naught is the radial load factor, and y naught is the thrust or axial load factor, which will depend on whether the roller bearings is single row or double row. Now let us also look at another term that he refers to as life of a bearing. Life of an individual ball bearing is defined as the number of revolutions or hours at some given constant speed which the bearing runs before the first evidence of fatigue develops in the material of one of the rings or any of the rolling elements. You can just call it the number of revolutions which the bearing runs before the first evidence of fatigue develops. So that is the life the bearing will serve. So before we have at the point where we have the first evidence of fatigue developing, then the bearing will still be serving its life. But once we have the first evidence of fatigue, then the bearing has finished its life. So that is the life of a bearing. And rating life of a group of apparently identical ball or roller bearings is defined as the number of revolutions or hours at some given constant speed that 90% of a group of bearings will complete or exceed before the first evidence of fatigue develops. So we always know that if it is 90% of the bearings that will finish that particular life, which could be the hours or number of million revolutions, then we will find that only 10% of a group of bearings will fail due to fatigue. Of course, we are talking about the rating life of a group. So when we say 90%, if we talk about hours for 90%, then we are talking about if we choose a particular series and there is it is a group of bearings. If we take about the number, their rating will be the number of hours that the 90% of that group will complete or exceed before the first evidence of fatigue develops. Then the term minimum life is also used to denote the rating life. It has been found that the life which 50% of a group of bearings will complete or exceed is approximately 5 times the life which 90% of the bearings will complete or exceed. Yes, so we have to note that. Then we may say that the average life of a bearing is 5 times the rating life or the minimum life. Yes. Let us also define reliability R, and this is the ratio of the number of bearings which successfully error million of revolutions to the total number of bearings under test. So we are saying reliability is the ratio of the number of bearings which successfully completed the error million of revolutions. Then we divide that number of the bearings, the total number of bearings under test. So if we have, for example, 100 bearings and we have, for example, 99 or 95, for example, which have successfully finished error million revolutions, then the reliability will be the 95 divided by 100, and that will be the reliability of a particular group of bearings. Then let us look at the basic dynamic load rating of rolling contact bearings. The basic dynamic load rating is defined as the constant stationary radial load in the case of a radial ball or roller bearings, or constant axial load in the case of thrust ball or roller bearings, which a group of apparently identical bearings with a stationary outer ring can endure for a rating life of 1 million revolutions. So this is the basic dynamic load rating, and this is going to be constant for a particular group of apparently identical bearings with a stationary outer ring. Then the dynamic equivalent radial load W, for example, for radial and angular contact bearings, except for falling slot types, under combined constant radial load WR and constant axial or thrust load WA, will be given by W equal to XV times WR plus Y times WA. V is the rotation factor, and which is equal to 1 for all types of bearings when the inner race is rotating, and 1 for self-aligning bearings when the inner race is stationary. Then this V is also equal to 1.2 for all types of bearings except self-aligning when the inner race is stationary. The values of the radial load factor X and the axial thrust load factor Y for dynamically loaded bearings may be taken from the following table. These are the values of X and Y for dynamically loaded bearings, and we will see that at the end of the day we need to know the type of the bearing, which could be maybe deep groove ball bearing. We could also need to know if it is an angular contact ball bearing. Then the specifications will therefore be WA out of C naught, which we said is the static load rating of a particular bearing, or the amount of load the bearing will carry when it is at rest. Then single row, 2 rows in tandem, 2 rows back to back. That is for if we talk about the angular contact ball bearing. Then you have WA, which is the axial load divided by the radial load. If it is less than E, and then we will take X as 1 and Y to be 0 for the deep groove. Then if we go beyond and we look at the angular contact bearings, then the value of Y will change. Likewise, if WA and WR, the ratio, this ratio is greater than E, then you need to take the value of X as 0.56 throughout, then the value of Y will always change. So this is basically required when you know that your bearing is going to support a radial load and also going to support an axial load or thrust load. Then the dynamic load rating for a rolling contact bearing under variable loads, we will see that the approximate rating or service life of a bearing or roller bearing is based on the fundamental equation. We see this is going to be L, which is going to be C out of W power K times 10 power 6 revolutions. And we can also say now the basic dynamic load rating C is going to be W, which is the equivalent dynamic load, times L out of 10 to the power 6, and everything is to power 1 out of K. And whereby K is equal to 3 for ball bearings, and it is equal to 10 out of 3 for roller bearings. These ones you have to always note them. This K will always be 3 for ball bearings, and it will always be 10 out of 3 for roller bearings. The relationship between the life in revolution L and the life in working hours is given by L equal to 60 times N times LH revolutions, whereby LH is now in million revolutions, then is in hours, then 60 is a conversion factor, then N is in revolutions per minute. So what you get will be L, which is the life of the bearing in million revolutions.